Hello everybody and welcome to chapter number 9 in statics. This is Professor Algara with our video for this chapter, and I'm going to be talking about the center of gravity and centroid. Those are the two topics that are going to be covered in this chapter. And I would say that this is one of the toughest chapters to understand here in statics. So I hope you can, pay attention, and hopefully the exercises will help us clarify everything that needs to be clarified. All right, so a body is composed of an infinite number of particles. So if the body is located within a gravitational field, then each of these particles will have a weight dw. The center of gravity, it's a point often shown as G or capital G, which locates the resultant weight of a system of particles or a solid body. From the definition of a resultant force, the sum of moment due to individual particle weight about a point is the same as the moment due to the resultant weight located at G. So we talked about it, basically what it's telling you that you could have a system with a bunch of differential of the weight, of course, and then all the sum of those weights will be, giving us a resultant weight, and that weight will be located in the center, and what we call the center of gravity of the object, of this solid model. And that's what we'll be doing throughout the chapter, basically developing, and utilizing these equations. We had something like this on chapter number 4. We barely talked about it, and you can go back to the video so you can see the explanation. Back then I told you that there was no need to worry because we were going to have a whole chapter just explaining on how to get this in the center of gravity or centroid. Okay. All right. So let's say you have a bar, right? And this is a bar, which has obviously its origin, and then you have very small pieces of differential of the weight, which is located at a point that we will call x tilde or type. We know that if you take all those little pieces and you put the pieces together, you will get a resultant weight or a total weight that is located to a distance that we'll call x bar. Okay, and this x is not the same one as this one. Okay, because this one right here, it's a location of the small differential, whereas this one is the location of the whole total weight, which we call the centroid, or the location of the total weight. What we need to know, if we take a look at this one and we want to get the total weight, right? We know that that total weight will be equals to the integral of all those pieces dw, small pieces dw. So what about if you need to find this guy? We could apply moment around O, and we know that if we apply moment around O or MO, that will be equals to x bar, which is the distance that multiplies to the total weight, right? If I apply moment O to this side, which has all the differentials, I have to know that I will have to integrate all those little pieces of x tilde that multiplies dw. All those pieces will have to be together, and this relationship will satisfy because obviously it's the same as I stated right here on top. Okay, if I solve this equation in terms of x bar, which is the centroid, what I'm looking for, I will get that is equals to all those pieces, or those pieces of moments divided by the total weight. Okay, and don't forget that we stated before that the total weight, it's equals to the integral of all those small pieces. So it'll be basically the total moment of the pieces over the integral of the total weight. And this right here is the definition of the centroid. Okay, obviously we're talking xy, and that's why we're only doing x. But if we have a y location, will be exactly the same thing. The location for y bar, will be equals to the integral of 0 to L of it's the same thing. And if you want to find z bar, it's exactly the same one. What is important about this is that we understand where the equation came from. At first we apply moment on both cases, and as I assume that it was exactly the same thing, then the moments will be the exact same thing, and I just solve for y bar or x bar or z bar. Something very important, and I have to stress it again, and I'm sorry about that, is that x bar is not the same as x tilde or tilde. I don't know how to pronounce that in English, and I'm sorry for that, but it's not the same, and you will see that a lot in the book. Okay, so watch out for that. The concept of the center of gravity, it's basically, or as we say, the location of the center of gravity measured from the y-axis is determined by equating the moment of W about the y-axis to the sum of the moments of the weight of the particles about the same axis. That's what we just did before, right? I took the sum of moments from one side, with the resultant force that multiply the centroid, and I know that that's exactly the same thing as I put all the small pieces of differential multiplied by the location of each one of those differentials. Okay, which is this. That's what I just did. And you can apply the same thing for y and x. So as I show you at the beginning, this one, it's exactly the same one as that one. And if you start with that, then the equation that we just saw will make sense. So if you want to calculate for x, y, and z, then the equation becomes the exact same thing. So if you want to find, and this is the beauty with this, if you want to find, we just talk about, the center of the weight, but if you want to calculate the center of the mass or the center of the volume, it's the exact same thing. We're just going to replace the weight by using volume, area, or length. Okay, it'll apply for all of them. The centroid is a point defined in the geometry center of an object. The centroid coincides with the center of mass or the center of gravity only if the material of the body is homogeneous. The density in a specific way in the specific way is constant throughout the body. Okay, basically that you don't have different materials or different bodies with different materials together. If an object has an axis of symmetry, then the centroid of the object lies on that axis. That is specifically like if you have a rectangle, a 3D rectangle, then the centroid will go right through the width, and in some cases the centroid might not be located on the object, as you have a whole combination of different objects or like a crazy shape. You cannot assume that it will be in the center. As you know, there was a table that I mentioned you about of determine figures like rectangles and square and triangles and things like that. So that's the base that you need in order to tackle the exercises in this part of the book. Okay, so the steps to calculate or to find the centroid of an area. So at first we need to choose an appropriate differential element dA at a general point. Generally, if y is specified in terms of x, we need to find a vertical rectangular element. If it's the opposite, then we need to use a horizontal rectangular element. We need to express dA in terms of differentiating the element, dx or dy. Then we need to find the coordinates of those points that we found, which is, x tilde and y, not x bar or y bar. Then we need to express all the variables, and we need to perform the integration, and then after that we will be able to calculate the coordinates of the centroid. And obviously, as I always say, the steps will be the same thing as you calculate the center of gravity or the center of mass, but more importantly, these steps will become clearer by doing a few examples, and that's what we're going to do now. All right, and then we have the following example. What we need to do is actually to follow the steps that we laid out in this slide. So at first we need to choose an appropriate differential element d8 at a point xy, and then usually, like I said, it's easily expressed in terms of x. If it is expressed in terms of x, then we should use a vertical rectangular element, and that's exactly what we'll do with this. Since it is expressed in terms of x, we will choose a small piece or small strip in which we're going to work on it or something like that, and that strip has to be placed into terms of a differential of area. And just by looking at it, it'll be a differential of area which is given by the function dx, and I know that y is actually given by the x cubed, which is x cubed dx, and that will be my small differential of area. So far we did second one. Then after that we need to determine the coordinates of the centroid of the rectangular element that we just chose, and then after that we just need to use the equations that we learned before, which are this, in order to get the coordinates of the centroid, which is x bar and y bar. Okay, so moving along to the next slide, that's exactly what we're doing. We need to find the location of that differential, which is right in the center of the script. And like I told you, in the book you will see this symbol a lot, which is totally different than x bar. This is the centroid, and this one right here is the location of the differential that you previously calculated. At the end of the day, we're looking to apply the equations of of the area of x, and I will use the same symbol, dA, over the differential of dA of the area. We previously placed dA in terms of x. We just say that dA was going to be equals to x cubed dx, being put in terms of x's and all those things. So all we have to do is just plug into the equation. So this symbol, it's actually the location that is equals to x, and the location in the y direction will be equal to half of that, as you might know from the table that I told you in chapter number 4 that you should go and look at, in which you will have the common centroids for common figures like triangles and rectangle and things like that. So you will know that the rectangle actually goes in the center. So that's why the location of that centroid will be the function divided by 2. I know that y it's equals to x cubed, so therefore the location of this guy will be equals to x cubed over 2. And then with that, I just have to use the equation. So let's just give numbers to the equation so you can start looking at it. So I know that the location of x bar will be equals to this x, which is this, and then dA, like I said, we just calculated, and that was x3 dx, and this is going from 0 to 1 because in the previous picture I knew that this one is 1 and this one is 1 too. Okay, this will be over the whole integral of the dA, which is x cubed dx. And then once I have that, all I have to do is to integrate so I can get the value. This would be 1/5 x to the 5th, right, over 1/4 x to the 4th, and all of this is evaluated between 1 and 0. This one 2, and 0 to 1. When you evaluate that, you will get that x bar it's equals to 0.8 meters. Boom, finally we get the first result. Then now we go with y bar, and that y bar will be equals to, I will just write the equation as well. It's y bar dA over the integral of dA. Okay, y, not y bar, sorry, y with the symbol. That's why I don't like that symbol, but anyways, it's the way it is in the book. You know that symbol, it's y divided by 2, which is equals to x cubed divided by 2. So if I plug in into the equations, I will get the location of that y will be, like I said, x cubed divided by 2, which multiplies the a, which is a cubed dx, and this is from 0 to 1 over the integral from 0 to 1 x3 dx. Okay, so now I just have to integrate, and what I will get is that on the top is 1/14 x to the 7 over 1/4 x to the 4th. Both of them need to be evaluated between 0 and 1. You know, when you evaluate both of them, you will get that your y bar, it's equals to 0.2857 meters. And that's the final result. Okay, so you got x bar and y bar. The important thing with this, and remember, this is just approximation. We have something that was given in terms of a function, and we use the function, we use the differential of the area, and we use the steps that were developed previously, and we got the result. Okay, so that will bring me to example number 2, which basically you have the shape, it's very similar, and you need to find me the a, you know, the differential of the area, and also the location of that differential. If you do that, then I will give you extra points that you can use maybe for the final exam or the first exam. You know, doesn't really matter. Okay, just make sure you shoot me an email with just the results, and I will award you with the extra credit for that particular exercise. Moving along, we're now going to get into, you know, the center of mass or the center of gravity of a composite body. Okay, so consider a composite body which consists of a series of particles or body, as you can see in the picture. You know, we know that, for example, and we always use weight because it's easier. You know, that resultant weight will be the sum of all of those little weights, and if you want to use the moments, it's the exact same thing, as long as you know the location of each one of those weights. You know, as we developed at the beginning, we know that the moment of that will be the resultant weight multiplied by x bar, which is the centroid, and that will be equal to the sum of all those little particles multiplied by the location of each one of those particles, and at the end we will get that equation. What is very important about this is that basically you can do the same thing with the moments, but now around axes like x, y, and z, in order to find the location of that centroid x, y, and z when you have multiple bodies or multiple particles in the same system per se. And you know, that will also work exactly the same thing for mass, for the center of mass, just by replacing the weight with the mass in these equations. Okay, very important. So the concept of composite body, like I said, is a combination of different particles or a combination of different bodies. What's happening here, guys, is sometimes you will have a weird shape, right? And that weird shape is not on the table that you have, the table that I keep talking about. Go back to chapter number 4 and you will see the table. It's in the back of your book. So that table has, you know, the center of gravity or the center of mass, the location of those things. They are laid out on a table for specific figures, such as rectangles and squares and, you know, triangles and things like that. For example, from distributed loading, you know that the location of this guy, of the central, will be 1/3 from here, right, from the right angle, or 2/3 from here. If you are in a square, will be right in the center. If you have a rectangle, so on and so forth, it's the same thing. If you take a look at this particular picture, you can divide that into different components like this square, then the triangle, then half of a circle, and then you will subtract the whole that you have. And then if you take a look at this picture right here, you have a triangle and you have a rectangle. You have another rectangle here, another triangle, and a huge rectangle right there in the middle. So what I'm trying to tell you is that if you want to find, you know, the center of gravity of a complex figure like this or a composite body, you can divide that by multiple elements, and then if you use all of that into the equations that we just discussed, which is this, then we can get x bar, y bar, and z bar, because it's the sum of all of those things. Okay, those little pieces multiplied by the location of those pieces, and that is divided by the whole thing. If it's weight, the whole weight. If it's mass, the whole mass. So let's just read what it says. This can be done by considering each part as a particle and following the procedure described in 9.1, the one that we just talked about. This is simple, it's effective, and practical, and a practical method to find the location of the centroid or center of gravity of a complex part, a structure, or machine. What are the steps for analysis? And just take a look at this, because this is very important. And remember, I told you at the beginning of the chapter that this is one of the toughest chapters because it's just crazy. But believe it or not, if you follow those steps, things will be easier. So you need to divide the body into pieces that are known shapes, you know, things that you can find, for example, in the back of your book. Don't forget that holes, they need to be considered as pieces with a negative weight or size. Then we should make a table, you know, with the first column for the segment number. Then the second column should be weight, mass, or depending on the variable that we're talking on. And then after that should be the location of those things, and then the multiplications of those things. And once you have the table all built up, then you should find all the sum of those multiplications over the sum of the whole area. And if it's weight, what we're talking about, though, then it'll be the sum of the multiplication of those particles, those little weights, multiplied by the distance divided by the total weight. Obviously, as I always say, it'll be straightforward after doing the example. And I just want to stop for a moment. Guys, don't forget that you need to read the book, okay? This is just helping you and pushing you into understanding this whole thing, okay? So that's example. We have 3 elements or 3 blocks that are assembled as we see. Then we need to find the center of the volume of the assembly, and then we just need to follow the steps for analysis. So in this problem, the blocks A, B, and C can be considered 3 pieces, okay? The first piece would be this triangle that obviously is in 3D and goes like this. Then we have a rectangle that goes like that. Then we have another triangle right here. Don't forget that these guys are 3D and we've been asked to find the volume. Okay? Something very important, and you have to remember that when you have symmetric parts and you're locating the centroid will lie on the axis of symmetry. Okay? What I'm telling you by looking at this, look at the parts in 3D, and it's very important that you look at the parts in 3D because that's what we are about to solve. Okay, so what do? We are going to need to lay it out on a table, and let's just look at the table. We have elements A, B, and C, which is A, B, and C. Then we have the volume of each one of them, volume A, B, and C. Then we need to place the location of the centroid in X, Y, and Z, and then the multiplication, okay? Let me go little by little and back off a little bit so you can understand. So first step, we need to calculate the volume. So if we go with element A, we know that the volume will be base times the height. So we know that the base, it's equals to 1.5 1.5 multiplied by 1.8, which is the height. That has to be divided by 2, but it also has to be multiplied by the width, which is 0.5. So that's why you have 2 0.5, and that's equals to 0.67. Now you will plug this into its corresponding cell, right? Then after that, we go with B. B is a rectangle, which is base times height. So the base would be 2.5 right here times the height 1.8 right here, and then it has to be multiplied by the width as well because it's a volume, and then we get 2.25 that goes right here. Okay, so now we do with BC as we did with the first triangle. You know, I don't have to repeat that, but BC will go right here. Remember that you need to know, in this case would be total volume over the little volumes multiplied by the location of those volumes in X, Y, and Z. Okay, if we move into the table, we need to find the location of the centroid for each one of those elements. Okay, and the location of the centroid of this one, you know that is 1/3, you know, of the base, looking from here. But also, I will move that right to the center. Something like this. That's a triangle. And the centroid has to be somewhere around here. So how do we do that? So where is the location of Y bar, for example? Y bar would be 0.5 and then 1/3 of the next 1.5. So that's why you have 1 in the X, right? This axis. Remember, it's a location. We're focusing only on the triangle. What about white? So white would be right in the center of the width, right? Because it goes right in the center since it's a symmetrical part being watched from Y. That's why it's 0.25. What about Z? Well, same thing, is 1/3 of that measurement, and that's why you get 0.6, which is 1/3 of 1.8. Okay, now we go with B. In B, and remember, we're going little by little. B right here, the X location. With B, it's a lot simpler because it's right in the center. So in the X direction will be 0.25, which is half of this guy. Then in the Y direction will be 1.25 because basically it's 2 meters plus 0.5 divided by 2 to be right in the center. And then finally we have half of 1.8, which is 0.9. Now for Z, you can figure it out. It's also given by this and the location. You know that by now, so I'm not gonna get into that. So once you have that figured out, all we need to do is to multiply this guy times this guy, and that will go right here. Then after that, you need to multiply this guy times this guy so it can go here. Because please don't forget that you're using this equation, okay? For X as well, for Y as well, for Z, okay? And that's what we're doing because we're solving a 3D problem. So once you do that, you will multiply the volume times Z, and that will go right here. Once you do the same thing for A, B, and C, you then will have the sum of all of them. Now you have the sum of the total volume, the sum of the multiplication in X, multiplication in Y, multiplication in Z. And you will take that into the table so you can use the equations. So like I said, the center of gravity will be the location times the volume. That's what you got for this. That's why you get this over the total volume. You will repeat the same thing for Y and the same thing for Z, and then you will get the coordinates of your centroid. And voila. That's how you solve the exercise. So guys, we have just completed one of the toughest chapters in the book. This is quite important, but if I just want to go back to let you know that it's not, I mean, it's tough to understand it, but once you get the geek behind it, it'll be a lot easier. The whole thing with this is that when you have complex structures, you can start dividing those structures into something that will work out for you, and something that is easier to manage and easier to calculate. Nowadays, we have programs that will calculate the centroid just by you doing the 3D model and everything. You will be able to calculate the centroid, but I need to show you how that centroid is calculated by hand. And obviously, it helps with your whole engineering preparation. As I'm always telling you guys, you can shoot me an email so we can go one-on-one, in case you need further help. Don't forget to read the book. Don't forget to go through my notes. And if you still have doubts, then contact me and we'll, sort it out in order to help you. Thank you very much for watching all my videos. And if you don't have any questions, then I will see you in the next video. Thank you.